Okay, one more announcement. Forgetting what I was talking about on Monday, there is no first problem set. Just for simplicity, so that you guys can focus on the projects. I think that's more important. Otherwise, there will be this confusion on what you should do. Yeah.
I know there's like a couple of places where they're talking about the requirements for the final projects. Can we just get a clarification about what the actual formal requirements are?
Yes.
So like length, date, due.
I'm coming back for this formal announcement. Yeah, no, so the formal requirements are that we would wish you to submit just project report. There's no posters. The deadline is midnight on the December 12th, that's Wednesday. There is no extension that you could have used during your presets, but it is the deadline. We're not going to be accepting things after that, but we have to grade 100 of these. We would wish you to stay within 5 pages plus references. If you do 5 pages and 10 words, it's okay, but please don't go to like 5 pages and then think, oh, you know, maybe 10 pages is okay. That's no. Any other questions?
Well, team projects.
So for the team projects, we are expecting longer, but less than 10 pages. Question? Also. Okay.
Thank you.
Did you start? You started?
I'll check, but I think it's. Actually, you have a minute left. Yeah. Okay. CVMM YouTube. Switch to live streams. It is streaming.
5 pages do not include references.
No. Yeah. Oh, I'll go get new battery. Unless there's some. I'll be back in 2 minutes. Yes, the other thing is if you have like a huge amount of plots, then you can put them at the end, but no extra text. No what?
Okay, so the batteries are dead. So I apologize to those watching. So today we're going to do a sample complexity of neural networks. What I'm going to do is I'm going to first discuss different notions of complexity you can consider. I will do one proof, which is going to be about 5 lines. This is a classical result from 2003. Then I will just state some of the new results, which are more or less state of the art. At least as of the last time I checked archive, which is already off. Let me start. I'm going to consider a neural network f sub w of x, which is nothing but w, a matrix w, let's call it L, and then a nonlinearity. So think of this as ReLU or some Lipschitz function. I will specify whenever this is important, WL minus 1, and so forth until sigma of W1 x. Okay, so this is our function. I don't consider the loss function. You can choose that arbitrarily. It is important for some questions, but not for the questions that we will study in this lecture. If I have time at the end of the lecture, I will discuss some geometry of the landscape in terms of the parameters that will tie into this discussion. I'll draw some pictures with at least my understanding of the geometry of the landscape for neural network. My very limited so let me proceed. So kind of the first thing that you can do, and as you will see in a second, this is really a very loose thing to do, is just to go in the route of VC theory, or VC dimension. So if you go in this direction, I know I haven't really discussed the VC dimension, so let's just, for those who know what the VC dimension is, you can try to understand the VC dimension or pseudo dimension, if these are real value functions, of this class. And typically the bounds that you get from VC dimensions are something like a VC dimension divided by n. And now the question is, what is the VC dimension of a class of functions of this form? Now I have to specify what is exactly, what is this class of functions. So I'm going to fix the architecture. It's just a feed-forward architecture. Let's just say no bias. It's just what I've written here. And you fixed all the dimensions. Okay, so the dimensions are fixed. The only thing I'm doing in this lecture is changing the weights. So you fixed the architecture and you're changing the weights only. So now this induces a class of functions. So let's call it F, I don't know, NN, neural networks. As you vary the weights. Okay? So now the kind of the state of the art result, and this is a paper by Bartlett et al. In I think it's in 17, that the VC dimension is equal to, so let's use some letters. So let's say L is the number of layers, and let's say I'm gonna just put a pound sign, is the number of parameters. So the number of parameters is just the sum of the product of the dimensions of the matrices, right? Just the number of weights, number of parameters of weights. Then the VC dimension scales like, maybe pound sign is not a good idea. Give me a letter, kappa. Kappa is the number of parameters of the weights. Then the VC dimension is scales something like order of L times kappa times log kappa. Let me just double check this. Yes. So if you look at that paper, there are about 5 authors here. There are many results here. I've just written the one that's easy to state. Okay, this kind of the simplest.
This 2017 or?
So 2017, yeah, just last year.
But the original result was much
So,
good.
so the one can get kappa squared. That's a very old result with a kappa squared. Some dependence of that form follows from results by Goldberg and Jerem, I think, in 1993, where there's a very genetic statement. If you have a class of functions that take, that many arithmetic operations and multiplication and division, subtraction, whatever, to compute, then the VC dimension of that function class has to be bounded. You can't have too much expressivity if you bound the amount of operations that you're going to perform. So it is of that flavor. This result is more subtle, but this is kind of a state of the art.
Sasha, just curiosity. Bartlett had a result on similar one, but not as good, in the 90s or?
Yes, that's correct.
Okay.
So in the 90s, and I think it was the kappa squared result.
Okay.
Yeah. Okay. So this result is typically being dismissed kind of as this cannot explain the performance of neural networks because typically one takes many more parameters than data. Or I guess I heard that you should take 10 times more parameters than data.
I told you.
This is kind of a rumor, okay? So then in that case, this is automatically a vacuous upper bound, right? And so this was already understood back in the 90s. So if you take a neural network that is large enough, somehow it still works well, but the VC theory doesn't explain it, okay? And that actually was the part of the impetus to the large margin theory, part of the push to develop the large margin theory, which we already discussed. So I just want to state this as a kind of this is the crudest thing you can do, okay? If someone tells you, oh, we have to rethink neural networks because this bound is loose, well, I mean, this is just one bound, okay? This is just one loose result. Yes?
Is this for ReLU specifically?
This one is for ReLU, but the result there is actually very general. So it can be a polynomial of degree q, and then there's q that's going to show up here.
It can't be like a sine curve.
Probably not. Yeah, so it has to have some regularity. Okay. All right. So let's end here, and we know that this is not the end of the story because we already know that perceptron is a one-layer neural network without a hidden unit, and we've got a perfectly fine result in our first or second lecture that I taught, and it was dimension independent. Dimension independent now for hyperplanes, dimension is exactly the VC dimension. And that means that we already have an example where VC theory is clearly too loose, and we know this. Okay? So VC theory, in its most basic form, maybe I shouldn't say that VC, Vapnik-Cherenkis theory is the whole theory. Okay, there's the Vapnik-Cherenkis dimension approach. It is really like a worst case bound. Okay, you're assuming the worst case distribution. You're requiring the result to hold for all distributions. You're not using anything about the problem. Okay, so that's not the only approach. The other approach that we've developed is the kind of margin-based. Margin-based approach, and that, if you remember, that allowed us to talk about real valued functions, and not just take the, okay, for classification, we take the sign of this function, but if we care about the scale now, because of the margin, then we can get results something like 1 over gamma times the Rademacher averages of the class of functions, right? So this margin-based bound would give us something like 1 over gamma times Rademacher averages, or did I use just the R hat of F and N. And here, when I write this, what I mean is that this is projected on the data, right? This is evaluated at the x1 through xn. Okay. And we saw that for for linear class, so this was the example, if you take the class of linear functions, which is just a class of x maps to w times x, and the w now is a vector, and it's bounded in the Euclidean norm by 1, then, and you did this for the homework, and I did it in class, and some people still ask questions about this, then Rademacher averages of f lin is bounded by 1 over square root of n. Right? This was a very simple computation where you take w out by linearity, write it as a dual norm, use Jensen inequality. That's it. Okay. Okay. So again, the idea now is that somehow the size of the weights matter, right? The size of the weights is not reflected in this result. This result is purely about how this class of functions realizes different sign patterns. And you can realize sign patterns, that's what VC dimension is counting. You can realize sign patterns by stepping 1 millimeter above the axis and below axis, above axis, below axis. The function is almost flat, right? So by almost zero function, you can realize different sign patterns. Now, this doesn't allow you to do that. This type of analysis says, if I'm assuming gamma margin, now I can talk about functions and how they go up and down on some scale. And if the function is almost flat, it's not an interesting function. Rademacher complexity is small. Okay, so that's the rough idea. Okay, and it's the same thing here. If you take w's to be really small, right? Imagine that you take all these w, the entries of w to be minuscule, then you're getting an almost constant zero function everywhere, and that somehow for margin analysis that is not a complicated function. So now the whole game is to mimic this type of analysis, but for neural networks. Okay. So what do I mean now by sample complexity? Well, let's go back to this example. So here I know that this object is 1 over square root of n, and if I just looked at f for linear functions, then I knew it would be 1 over square root of n times 1 over gamma. So if I want to drive this number to be epsilon, right? Remember, this is the gap, the upper bound on the generalization error, right? So if I want this to be epsilon, then how large do I need n to be? Well, you set, so it's 1 over square root of n times 1 over gamma is equal to epsilon. You invert and you get n needs to be at least 1 over gamma squared, right? 1 over, let's write 1 over gamma squared and 1 over epsilon squared, right? So 1 over gamma times 1 over square root of n is equal to epsilon. So you get n needs to be at least 1 over gamma squared and epsilon squared, right? So that's roughly the sample complexity, right? So that's the definition of sample complexity. How many examples do you need to get an epsilon accurate solution in terms of, let's say, generalization error, or if it's ERM, then for excess loss. Now, if this was some B, then what would happen? Well, this would be just B here. Then you would get a B here. And then you would get a B squared here, right? So the only thing that changes is that the radius gets squared. So now, this is where kind of things become interesting from my point of view. Is what should be the measure of complexity for neural networks, and will we get that measure of complexity squared, for instance, or maybe to the 4th power or some other power, if we talk about sample complexity, right? So I want to understand what are the true ways in which neural network complexity can be understood, right? And there is not a single way. Right? There are multiple ways. Some of them are dominating another one. But in general, there are other measures that are incomparable. Okay, so we're not going to shoot for one golden result. We're going to describe a bunch of results. Right? All right. So another thing to note is and this is a long discussion that we have all the time in the community. Is the purpose to get a bound that's is the purpose to get this number to be smaller than 1? Okay, you would like this to be smaller than 1, right? Because generalization error is bounded by that number. Let's say this is proportion of correct predictions, or right? But without understanding really the whole distribution it's very difficult to do so. It's very difficult to get a sharp bound that matches what you see in practice. So what you can hope to do is to provide some measures of complexity that seem to be correlated with the generalization performance. Okay, that somehow qualitatively have the behavior that you observe in practice, even though maybe the constants are not there. Okay, just as a preface. Okay, is that clear? All right. Okay, so so what is the first thing you want to do to mimic this Euclidean norm? Well, the first thing you might try is to say, okay, let me take the Euclidean norm of my neural network. Okay, I don't know what to do, how to do this. Let's just assume that these are values. Okay. Yes.
So when you say that looking for a measure of like complexity, is it different from Rademacher averages? Because we actually, when we introduced them, we were looking for a measure of complexity.
Yeah, you're right. So that's a good point. So no. So what I want to do is I want to define some measure of complexity. I'm going to call it conv of a function fw. Okay, which is purely going to be a function of the matrices w. Okay, it's not the only way to measure the complexity of the function, but it's a way. So it's going to be some complexity comp of w1, wl. Okay, and then I'm going to, given this measure of complexity, I'm going to define a ball in the space of neural networks. So this ball is going to be f neural network of radius 1 is going to be the set of fw such that complexity of w1, wl is bounded by 1. Okay? So this is I define a measure of complexity, and then I take functions that have complexity bounded by 1, right? So if you want a visualization, this is your space of neural networks, unbounded. You can scale w as large as you want. Here's the origin. This is the zero function. The zero function is included in my set because I can set all of them to be zero matrices, and I get the zero function. And now I'm going to define some measure of complexity which has a certain shape. It need not be a convex shape. I'm just going to draw a ball in that space. Okay? Is that clear? So even though these are functions, I'm thinking of measuring the complexity only with respect to the weights. Right? And then I'm going to consider different radii. So I can cover the whole space. Any neural network will have some complexity, so it has the smallest ball in which it lives of some radius. Okay. Now it turns out that it's enough to just consider radius 1 ball, because then what you can do is you can just take a union bound and say that my result holds for all radii, and so whatever the function happens to be, the result will be given by the complexity of that function. So that's I train my neural network. It's data dependent. It happens to be here, but I know that for all functions, some closeness of empirical and expected quantities will be achieved. The level of degradation is going to depend on the radius. So I'm not going to go into these details. It's just a union bound, but let me just say that it's enough to consider radius 1. Okay. Okay. What is more important is what is the measure of complexity. So what is this comp? So one thing that you can start with is kind of attempt 1, 0. We'll say attempt 0 is to say, okay, so complexity. I'm just gonna use W to denote the set W1, WL. Okay, so these are all my matrices. Okay, and F sub W is exactly parameterized by these matrices. So I'm going to say complexity of Fw is going to be defined as, okay, so what's the analog of this? What's the analog of a Euclidean norm for matrices? It's a Frobenius norm, right? Now, okay, now I have L of them, so what do? Maybe I just string them together, right? So maybe I can take my complexity to be square root of the sum of Wj squared. This is the Frobenius norm. So Frobenius norm, if you're not familiar, just take the matrix, think of this as a vector, and take the Euclidean norm, right? So it's just the sum of the squares of the entries and then square root of that, right? That's the Frobenius norm. So, okay, I mean, this is the kind of the first thing you can think of. And then I can try and work hard to show that Rademacher averages of this class with that complexity are bounded in some nice way, right? Now, I'm going to argue that this is not even, I'm not even going to try to do that, because this is not the right notion. And the fact that this is not the right notion, I'm going to argue as follows. So observe that I can multiply a whole matrix by a constant, let's say 100, and then divide another layer down by 100. So one layer goes up by 100, down one goes down by 100. What happens to the Frobenius norm of that matrix? It changes quite a bit, right? What happens to the function being computed? It stays the same, nothing changed, right? We have positive homogeneity. Okay, so I'm assuming that sigma is ReLU. Let's just assume that sigma is ReLU, right? Then, yes, so I should preface this whole discussion by just pick sigma to be ReLU. Then any constant you multiply here comes out linearly if it's a positive, non-negative constant, right? And so somehow that's not the right notion of complexity, right? Now, neural networks have a lot of symmetries, a lot of invariances. You can do different things to the weights, and then look at the function. Oh, it's the same function. Okay, so that's an invariance. And of course, you would like ideally to have a complexity notion that doesn't care about these invariances, right? Because we're looking at the weight matrices, and if different weight matrices produce the same function, then these weight matrices, these collections should have the same complexity, ideal. So at least this kind of a very basic notion of invariance to these transformations are not captured by this norm. So what's a way to fix it? Yes? Multiply, great. So in fact, yes, so attempt 1 is to define a complexity notion, Fw, which is the product of the Frobenius norms j from 1 to L. And it turns out that this can be used to show that Rademacher averages of such a class are 1 over square root of n times, unfortunately, 2 to the power number of layers. Okay? That's the first result, and then we'll improve that. So I will state a bunch of results where that can be improved with a caveat, okay? With some additional assumptions. Okay, so this is a good measure of complexity. Let me actually now start by writing down different matrix norms, just to get you up to speed. If you don't remember your matrix algebra, so we know the Frobenius norm. I don't have to define this. let me define let's take a matrix A, and I'm going to define a 2 norm. I'm also going to, so this is called the operator norm, or spectral norm, or 2 norm. So different people use different notation, and this is just the maximum singular value of the matrix A. Okay, so if you don't remember what this is just the square root of the largest A. So the largest eigenvalue of A transpose A, if this is a real matrix. Okay? Is everyone comfortable with these or not? Not really. More or less? Okay, there's a general there's a generalization of this, which is Schatten norms. Let's say for p greater or equal to 1, and that is, let's call it like that. Now, p. Now, there are so many different sub p norms that you have to be really careful to know what exactly that means. Okay, so the Schatten p norm is just the so think of this as an LP norm on the vector of singular values, right? So you take the vector of singular values, you look at its p norm. Right? So that's just a 1 over p sum of sigma to the p, sigma I from 1 to. So how far do I need to go? I need to go to the minimum of whatever the dimensions are. So let's say A is, let's say it's a real matrix for simplicity. D1 by D2, then it has to go to the minimum D1, minimum with D2, okay? The rest are 0, okay? So that's a general Schatten p norm. And in particular, the Schatten 1 norm is known as, anyone? Nuclear norm. So this is just the sum, right? So p is equal to 1 is just the sum of sigma i's for the matrix, right? Sum of the singular values. It's also called the trace norm because you can write it as a trace. Yes?
A infinity is A2.
And the infinity is A2. Yeah. Okay. Yeah. Sorry. Okay. Good. Good. Thanks. Right. So I'm going to erase this too, because then it will. Otherwise, it clashes with this. But if you write Schatten p equals to 2 norm, then it becomes Frobenius norm. So Schatten p equal to 2 norm is the same as Frobenius. But the infinity one is the max, and that is the operator norm. But sometimes it's called the 2 norm because it's the, okay, so you know the definition. You can interpret it as the ratio how A stretches a vector x, which is bounded in L2 norm by 1, and that's why it's called L2 norm, right? So it's 2 to 2 norm. Okay. So this is called the nuclear norm, or trace norm. All right. Okay. Then there are so these are measures. These are norms which work on the spectrum of the matrix, on the singular values. And now I'm going to talk about matrices that work on the actual values of the matrix. Yes?
It's really absolute values.
But they're positive, right? Because it's the square root of the eigenvalues of the positive semi-definite matrix A star H. So these are singular values, not eigenvalues. Okay? Yes? Yes. Why? Because you can, so this becomes squares, and then you just have to write out, okay, so you write out the SVD decomposition, and you'll see that Frobenius norm doesn't change when you rotate, and so you just end up with squares. Good. Other questions? Okay, so what do I want? I want to define entry-wise norms. Entry-wise. Okay, so there are kind of trivial ones where you take, you stretch it as a vector and then you take the LP norm, right? So they're kind of trivial. But let me write down a few different ones. So we're gonna say, let's say 2 comma infinity. So what does that mean? It means that you take maximum of L2 norm, of a Euclidean norm, maximum over, let's say, I. I'm going to use the MATLAB notation, I. This is the I column of the matrix. I'm taking the L2 norm of the ith column, and I'm doing the max over the columns, right? So all of these norms look like that. You take a matrix, you apply some norm, that's the first number that you see here. You apply that norm to the column, and then you apply the second norm to the resulting numbers, a bunch of numbers, right? So in general, should I write down this A PQ is the, okay, this is going to be painful. 1 over Q, so it's the qth norm. So now I'm going to take the sum of the Q over P, is that right? A I from 1 to whatever the D2 is, right? So up to D2. Did I do it correctly? This is the P norm. So you take the vector, you take the column, you take its P norm, right, which is the sum of entries to the raised to the pth power, and then to the 1 over P. Did I get it right? No. There is no. It's like that, right? Raised to the Q, and then that's the Q norm. Okay? Questions?
Sorry, I'm confused. Is the weight Wj a vector or a matrix?
Wj is a matrix.
So that you have multiple dimension output for your neural network.
I can make this one by whatever. Yeah. So the inner dimensions, okay, they have to agree, of course, but they can vary from layer to layer. And let's say it's a real value. Yes. So I should say that this is a real value. Real valued, which means that WL is 1 by whatever. Okay. Okay, so let me give you a flavor of how to prove things of how to say that Rademacher averages of such a class where you constrain the weights bounded by one of these norms, or product of these norms applied to layers one by one, right? How to control that sample complexity. Okay? And I guess you can try to make a living out of this. You can try different norms and try to prove an upper bound on random upper averages and write a paper on that. Okay. I mean that could be a game. But then of course you want to do kind of simulations and see if they correlate with somehow the performance of neural networks. And in fact, for the notions that I will describe, they do correlate. So there is some correlation, but it's not clear if this is any particular measure is a correct measure. Okay, it's one of the measures, one of the possible measures. Questions? Another question, by the way, is if you do prove this result, now you can ask, okay, does stochastic gradient descent keep that measure of complexity small or not, right? Because I could take an arbitrary network, it will generalize badly, and it will have a large complexity in this sense. It doesn't, of course, prove that it has to be small if it predicts well, but one can ask, okay, the kind of the ideal result will be I analyze stochastic gradient descent on a non-convex surface. It has this implicit bias of controlling some of these complexities. And I can show that random upper averages for that complexity are controlled, are small. That's kind of the ideal result, right? And so Tommy will speak a little bit about this. We know definitely for linear, for just the perceptron type of thing, there is implicit regularization. I defer to Tommy. Talk about this. For more general ones, it's there are papers this year. It's being investigated whether there is implicit regularization of by stochastic gradient descent in any of these senses. Is that clear? What I just said? So I'm going to just give you a flavor and the 5-line proof of how does one use these complexities. How can one do something to control random averages? And you'll see it's a very short proof. It goes back to 2003, a paper by Bartlett Mendelsohn, and it has this peeling flavor. So you have a multi-layer network. We have we need to consider random upper averages of these matrices. Of these neural networks with these matrices, bounded in some sense in terms of their complexity. What we're going to do is we're going to peel off one layer at a time and get a multiplier. And these will be exactly the multipliers that we had, like the product of some norms of the layers. Okay, that's how it's going to go. So I'm going to consider a class f I to be the class of functions. Here's what I'm thinking. You have a deep neural network, but I'm just going to focus on the ith layer. Okay. I'm going to focus on the ith layer. Now I'm gonna say that I've got some function of the input here. X comes here, right? It goes through the layers, and this node computes a real valued function of this x, right? As you vary the parameters, right? And this node computes some function of the x, and this one and that one, right? And now I'm going to do one more step. I'm going to say, if I go to this one node, to the next layer, can I understand the complexity, increase in complexity, due to combining these guys with some weights? Is that clear? So that's what I'm going to do. I'm going to define a function f of x to be the sum j from 1 to, so I'm gonna go over these guys. So that's the, let's say this is the ith layer, and this is I minus 1. So this is the dimension, I didn't define it, but it's clear from the context. Di minus 1 is the dimension of this layer, the number of neurons in that layer. Of W j, so that's the W, that's this this weight, times whatever the function was computed below. So it's Fj of x, where Fj belongs recursively to a class I minus 1, from whatever is computed by I minus 1 layers. And, okay, and this is a quantification on W. I have to constrain W somehow. And the proof that I will show works for an L1 constraint on W, okay? Let's say it's bounded by, not radius 1, but, so I said we're gonna only consider radius 1, but let's consider some radius b, some number b I, okay? So this is our class of functions. It's what a neural network can compute, right? It's what the ith layer node can compute, given that you tell me recursively what the nodes before can compute, right? Is that clear? Questions? Yes?
So when do you apply the linear back region?
Oh, yes, yes, good things. Where do I want this? It doesn't matter too much, but let me apply it. I think I'm going to apply it at the, let's see. Okay, so I have it here as applied. Thank you, good catch. As here, so like that. Good catch. Thank you. So sigma of Fj of x. Doesn't really matter where you put it, as long as it's consistent. The definition is going to be like that. Okay. And so here's the lemma, which we're going to show, just to give you a sense of what is involved in analyzing sample complexity. We're just going to show that empirical Rademacher averages of Fi is bounded by 2 Bi Rademacher averages of Fi minus 1. Okay, that's what we're going to show. Very, very. It's a straightforward computation. So as a corollary, the Rademacher averages of the actual neural network with L layers is going to be bounded by 2 to the power number of layers, and then the product of Bi, and then whatever the Rademacher averages of the initial layer are. But that's typically something like 1 over square root of n, right? As we saw in the example that I raised. Right? So something like 1 over square root of n, let's say, maybe depending on how you bound the x's, it might be a square root of log d, let's say, if you bound the x's in the L infinity sense. Okay? So let me put that square root of log d. This is not important. Okay. Now, what is Bi? So Bi is an upper bound on the L1 norm of these weights, right? So is this a row or a column of the W matrix? Is this a row or a column of a W matrix? It's a row, right? Because you go like this. Right, so you right, in the definition that I had before, it's the W matrix times the sigma applied coordinate wise to the vector of outputs, and now you combine for the new neuron, you combine the row multiplied by the output of the previous. Right? So now it's L1 for the row of the W matrix, and it has to be for every row. So how can I write it in terms of this? Take the exactly. So BI is an upper bound on the transpose of any J. Okay, let's make it like this: transpose, and then which one? Maximum of L1 norms, right? So it's L1 infinity, right? So what I'm describing here is a particular result which says if these norms of the weight matrices are controlled by some number, then Rademacher averages cannot be too bad. Okay, that's the upshot. Okay. So who wants to see the proof? Okay. Wow, that's more than I expected. This gives me energy. Of course, I didn't say who doesn't want to see. I didn't ask. It's like, do you approve of Trump or do you disapprove of Trump? All right. It's really 5 lines, so bear with me. My lines can be long. But it is 5 lines. All right, so I'm going to start by writing down the empirical, the left-hand side, right? So empirical Rademacher averages. Conditioned on the data, we have expected max of epsilon I from 1 to n data points, f of xi, right? These are the Rademacher averages where f belongs to fi, right? That's just a it's bad notation, sorry. Let's call it t. T. Right? So it's a correlation of the worst case correlation in expectation, the maximum correlation with the random noise, right? That's the complexity of my class of functions. Okay, let me in place. So I keep the 5 lines. I'm gonna write the definition of that. So that's a sum of Wj sigma of Fj of x. Yeah? Jawohl. Okay. So now I need to do. So what do I max over? All the possible ways of choosing W with norm bounded by Pi, and all the ways that I can choose F1 through Fj. Sorry, F1 through Fd1 in Fi minus 1, right? There are d minus 1 functions I compute here. I have to choose all of them, right? That's the complexity. Okay, so I just need to swap j from 1 to d1. I need to swap these two sums, right? When I do the swap, this is still equality. I haven't done anything, right? I'm just writing down same thing again and again. J from 1 to d1. Wj sum t from 1 to n epsilon t sigma fj of xt is t. Okay, so we lost 5 people just in the first line. There's still 4 more lines to go. You're gonna be alone by the end. All right. I haven't done anything. Really, I just wrote down this thing, right? Okay, now I'm gonna split this as a. These are summable to 1 in L1 sense. So if I take the maximum of this, if I take the absolute value of this, then I can split this into the maximum over J and the L1 of this. This is called the Holder inequality or Cauchy-Schwarz inequality, okay? I'm going to apply L1 here and L infinity here, which just means the maximum over J. So this is bounded by, so L1 of W's is of course just BI times expected max of over J over, okay, everything, that, and then max over J, sum of epsilon t sigma fj of xt. Okay? So I've chosen all my functions f1 through f sub d1, and then I choose the worst one. But that's just the same as just choosing one of them, right? So I can just collapse this to choosing one max over f, and this f is in f I minus 1, right? And then I have absolute value, right? Now, absolute value is just the maximum of this and minus that, right? So I have max, and then max over this and minus this. I can exchange the two maxes, and I just get twice, because whether it's epsilon or minus epsilon makes no difference. These are still coin flips. So that's just upper bounded by 2 bi expected max over f epsilon t sigma of f of xt, and then I do contraction. Remember contraction principle, I can erase any Lipschitz function, and that's it. So now apply contraction. It's a very simple proof, right? It's 4 lines exactly. And I didn't lose anyone. It's a very simple proof. Okay. So, this term is kind of inevitable, right? This is the product of some norms of the layers, and that was the choice, L1 and L infinity, L1 infinity. That's fine. This one is problematic, right? It's exponential dependence on the depth, and it's actually unclear how to easily fix it, but it turns out that there is a possible fix to that. So let me just write down the 4 bounds that were obtained in various papers in the last 2 years. Okay, and then I'm going to solve that. Should I maybe not erase this?
Any questions?
Most of the proofs that you'll see in the literature really just go like this. You peel one layer at a time. You want to understand the complexity of this composition. You try to understand recursively complexity of the inner functions being computed. One more layer, right? So you inevitably end up with some kind of a product type of complexity. It doesn't have to be, but so far what we see in the literature is of this type. And again, the product has this nice invariance to multiplication of one layer by a number and then another layer dividing by a number. When you have products of the norms of the layers, that doesn't change, right? So at least you're not suffering from the inconsistency. Okay, so some of the existing results I'm just gonna put them down without proof. Okay, L is the number of layers. We're done with this. Well, let me just use H to denote the max width of the network, which is the maximum of the inner dimensions of the network, okay? Including the input layer, which is the dimension D. Okay. So the result by how about this? Pur and Cerebro in 15 showed that the sample complexity can be controlled by the product of, it's what we said before, the Frobenius norms of the layers, J from 1 to L times 1 over square root of n. That's what you would hope to get. They got that times 2 to the L. Okay, so the exponential in depth. Again, this was somehow not satisfactory because people say, well, for deep it doesn't work, right? 2 to the 100, or it's already too big, right? It's not good. Okay, then in 17 obtain the product of spectral norms. Okay, so this is the operator norm, the matrix, which is a smaller value. Okay, so the operator norm is the largest eigenvalue. The Frobenius norm is the L2 norm of the eigenvalue, right? So if the spectrum decays, for instance, slowly, for instance, right, then the maximum can be 1, but the Frobenius norm can be on the order of the dimension of the matrix. Times, so this is J from 1 to L, times L, so far so good, times 1 over square root of n. But then there's another factor, unfortunately, which is the width of the network times the ratio of the Frobenius norm squared to the spectral norm, or the operator norm squared. So this can be as large as the dimension, and then you're summing up over a dimension, or sorry, this can be as large as, this is larger than 1, okay? It's larger than 1, you're adding them up over dimensions, over the depth, so you get at least square root of L cubed overall, and then there's a dimensional dependence on the width, okay? But this is already very close to kind of what you want. Okay, Bartlett et al. 17. This was a very fruitful year. 17. Product of spectral norms. Okay, that's very good, because these are kind of the smallest, in some sense, smallest of the Schatten norms that you can imagine. Times 1 over square root of n. So far so good. And then you can see that this is going to be something large. 3/2 sum j from 1 to L of the ratio of the 2, 1 norm, which I erased, or the definition I erased, divided by the spectral norm raised to the power 2/3. Okay. Again, this can be. I mean, it's not too bad, but it could be depth cubed, I guess, or okay. So you can figure it out. It's not hard. Okay. But again, this is very close to what you want. And then the result of Golovich et al. Again, 17 showed that you get a minimum. Everything here is up to log factors, by the way. So I'm skipping constants and log factors. Okay, forgive me. But it's a minimum of product of the Frobenius norms of the layers L, j from 1 to L, times 1 over n to the 1/4 power, and nothing else. So it's really, this is exactly what you want, but the rate is n to the 1/4, okay, instead of square root of n. And product j from 1 to L, the product of Frobenius norms, times square root of L over n. Okay, so you can essentially up to square root of L, square root of the depth. You get what you want with the Frobenius norm, right? Because Frobenius norm is worse than the spectral norm, but there is no. What's interesting about this one is that there is no dependence on the width or the depth. Nothing. Okay, it's just the product of norms of the layers. So this is really a dimension independent. It's very much in the flavor of perceptron, where you have an L2 norm of the vector divided by square root of n, right? Remember that result? The L2 norm of the vector divided by square root of n. This is the L2 norm of the layers, the product of them, which is natural, but not 1 over square root of n, 1 over n to the 1/4. It's an open question whether you can get 1 over square root of n. It doesn't explicitly, right? So everything is in the. I mean, you can, by the same token, you could say that perceptron result depends on the number of units. So Euclidean norm of the vector bodies, right? But well, I mean, it's a product of these numbers, right? But it only depends implicitly through how big they are. Right? That doesn't depend on the number of layers itself. Does that answer the question, or was there some other? Well, I'm open to suggestions, but this is kind of the best, I guess, you can get so far. You're welcome to try, right? I've given you tools to work, and you know, you can try and improve on this. I should note that if you use spectral norm, so that paper shows that if you use the spectral norm, then you cannot get nothing here. So if you use product of spectral norms, you should get a power of, let's say, the width of the network. Okay, and that dependence disappears on the width as you get to the Frobenius norm. So more precisely, it's the width to the power 1/2 minus p for the p Schatten norms that we were trying to control. If p is equal to 1/2, it disappears. So you can get a dimension-free result, dimension-independent result. But otherwise, okay. So questions. This is what I know about sample complexity of neural networks, more or less. What else do I want to say? I mean, one thing that hopefully, if nothing else, hopefully what you should take out of this is that the number of units is not the right notion, right? So if I succeeded at anything in this semester, it's to show that complexity that controls the statistical properties, generalization, for instance. Complexity is a subtle notion, and it can be the norm of the vector. It doesn't have to be the number of dimensions, right? So if anything, please take this out of this class. So I have 15 minutes. If you would like, I can do a little bit of kind of explanation about the feed-forward network and help you just to start visualizing the landscape, and that will probably lead into Tommy's set of lectures. Okay?
Maybe you can say a few things beforehand.
Yes.
About, first of all, in the case of one layer, this result reduces to...
In the case of one layer, it reduces to what you want, exactly. This one.
Yeah.
Exactly.
So,
Or a constant number of layers if you treat L as a constant.
so one layer, we know we can control that norm exactly.
That's right. So that's right. That's a good connection. So we know that gradient descent implicitly, if you start from 0, converges to the minimum L2 norm solution if you have a least squares objective. This is what Tommy will talk about. So what we know is that at least for one layer, gradient descent does control that complexity. And therefore, somehow the gradient descent is the right implicit regularization that leads you to small norm solutions which should generalize according to this analysis.
But so we know that for more layers is a similar complexity measure, where now you have the products of
That's right.
Frobenius
But it's not
norms.
clear.
But we don't know
We don't know
whether
if it's
gradient descent.
So there have been a number of
So
papers.
I will
this-
address this question.
Yeah, you will address. There have been a number of papers trying to argue this with certain success. By the way, what I forgot to say is this is not. This result has some assumptions. So I hid these assumptions, but there are some assumptions. So you can go into the paper and see. So it's not just assumptionless result. There are some small assumptions. They're weak, but they're assumptions.
One question is an intuition why products of norms?
It's just one way. I don't think this is the necessarily the right, or I don't think there is a right notion. I just think there are different notions, and this is one.
But there is a good argument for RLU networks that it should.
The scaling. So nice thing which we discussed is that it preserves the scaling property. So we discussed this.
So you could not have, for instance, the sum of them.
Yeah. So I did this. I did this example.
But this result holds for RLUs and other nonlinearities.
Yeah. With some assumptions, but with some conditions. Okay, so let me just end on kind of the way that you might think about the landscape. In particular, I'm going to consider the logistic loss function. So I'm going to think of f sub w of x as my function that I've defined so far, right? And now I'm going to think of a logistic loss which is for binary classification is just log of 1 plus x of minus y f of fw of x. Okay. So just to remind you, the logistic loss function in terms of the y times f of x looks like that. That's the logistic loss, and that's what people, cross entropy loss, and that's what people optimize in practice, right? They don't optimize the 0-1 loss because that's NP hard even in one dimension. I mean, not one dimension, even in one layer. Okay, so when you think about the landscape, I would like you to think of two pictures. So one picture is the set of parameters. So this is the space of parameters. Let me just say, W1, W2. These are not even matrices. They're just some entries in the W matrix. Right? So this is the space of parameters. And out of the board is going to be the 0-1 error on the end data points or logistic error on end data points. Okay? So this is going to be 0-1 error. So that's the 1/n sum of indicators whether f of fw of xi is not equal to y. The sign, whether the sign. Let's write it this way. Yi times f of xi is less than or equal to 0. Okay, that's the 0-1 loss. And this is going to be the logistic. So 1/n sum of log 1 plus e to the minus y f of x. Okay? Everyone is comfortable with that? All right. So these are feed-forward network without bias. So I'm just going to consider this one because it's simple. So I have one network. This point is a neural network. It's the set of parameters that define this neural network. This is the origin. Now, if I look at this direction, okay. If I look at that direction, which is just the scaling direction, what happens to the 0-1 loss? So this is the empirical 0-1 loss. What happens to the empirical 0-1 loss? It doesn't change, right? Because all I care about is the sign. If I'm scaling the w's by a number, the function scales by product of those numbers, right? So you scale every layer by a number. That number comes out to the power L, right? The number of layers. But the sign of the function doesn't change. We clear on that? So in particular, if I have 0 mistakes here, 0 mistakes, then I have 0 mistakes on the whole scaling direction. Okay. Now I can draw the same, I can put the same parameter here on the logistic loss. And now I can consider the line, same line. Now what happens on this line to the logistic loss as I scale w's up, or scale the function up? So I have 0 mistakes. So everything is on the correct side. So every y times f of x is above 0. If I scale the function up, I'm just moving f up. So I'm going down the logistic loss. Logistic loss is never happy. Okay? It will want you to go to infinity if you correctly classified everything. Right? It's never happy. The gradient is always pointing towards infinity. Okay? Or Okay, so you can visualize the profile on this line. Again, this is the zero mistakes line. The profile goes like that and decreases, keeps decreasing to infinity. Okay? Okay, and now the next experiment is start rotating this line. So rotate it until you hit one mistake. So it's a set of parameters. I'm being loose in terms of what exactly you're doing, but you can imagine doing this. You start rotating until now you have one mistake. On this whole line, you have one mistake. Okay? And now you start rotating further. Boom, you hit 2 mistakes. Boom, 3 mistakes, and so forth. So you can kind of visualize this landscape for this loss as being these steps that, if you're lucky enough, you've reached the zero. Now, what happens on this line?
So it's like a deep canyon with steps going up.
With steps going up, that's right. That's right. But something interesting happens on this, for this one. And I'm only considering the scaling direction. There are many directions in which you can go, and many of them are interesting and non-trivial, but I'm just considering the scaling directions. What happens there?
It's penalized for being overconfident.
Yeah, so it's happy on n-1 points. It's happy. The loss is small. But there is one point for which the loss is large, and it's getting quite large. So as you scale, at some point, this single mistake will overcome the n-1 correctly classified point, and the scaling direction will want to push you out, towards the origin, right? So along the ray, there is a saddle. I don't want to call it saddle. There is a point. If you constrain to the minimum to that ray, then it's a minimum. Okay. So you can formalize this with math. Okay. Okay, then there are two mistakes. Maybe it's like that. Okay, you can think of connecting this path of where you have in the outward direction from the origin, you have a inflection point.
But in your picture, there should be a pole or something, right? That is your mistakes of the line of minima.
Yes, exactly. So it goes. It's like this, right? I mean, the whole thing is like that, right? It goes to infinity, right? So it's an interesting surface. If everything is perfectly fine, like if everything is perfectly classified, you want to go to infinity. As soon as there is one mistake, there is a point where you don't want to go up, right? So there is some regularization just from the fact that there are mistakes. So it keeps you at bay just because there are mistakes.
It's a deep canyons that
Right.
is slightly slope downwards towards infinity with steeper and steeper.
Yes, so
walls as you-
that's the next thing that I wanted to say is okay, so you have this kind of a ray of hope, let's say, this ray of hope. Okay, it's the ray where you have no mistakes, right? If you go far enough and you look around, it's pretty steep on the logistic loss, right? Pretty high up, because the value of the logistic now, because of that one mistake, is very large, right? So I mean, of course, this is the space is larger, but I don't know how important that is. But I mean, you can see that it becomes hard to find the minimum if you have large scale weights. It becomes hard to find this region. Okay, I'm being not mathematical here. Okay, I'm just trying to help you visualize this. Okay, I mean, it's just it's just a bit of to start you thinking about what you want to optimize and what you are actually optimizing, and understanding what gradient descent does on that surface is it's pretty difficult. That's all for me. You're in capable hands of Tommy Poggio from now on. He will start on Monday. Yes. Yeah.